my name is Kevin, and I'm one of the co-founders of Nervos project. So I can just take a few minutes to talk about, what Nervos project is. So I think a lot of you guys probably have a Bitcoin background or very familiar with Bitcoin. So if you think about, Bitcoin like in BTC and Lightning Network, so essentially BTC is a very secure store of value, and then you have, Lightning Network as a transaction system, right, to do efficient transactions. So what we're trying to do is pretty much inheriting this philosophy of BTC Bitcoin. So we also have a very secure layer 1 protocol. It's called Nervos CKB. But instead of just can express payments, Nervos CKB can, just like Ethereum, can support smart contracts, right? So just like Bitcoin is a store of value, the value proposition for Nervos CKB, the layer 1 protocol, it's store of assets. The reason that we do this is we feel like once we have like a multiple layers, like a Bitcoin Lightning, then the base layer has to be a good protocol not designed for transactions, right? The reason is, when all the transactions are pushed to layer 2, then you want to make sure your protocol can still provide security to the assets on top of it. So if there's 0 transactions on Nervos CKB on layer 1 protocol, then we're going to still be secure, right? Whereas, other smart contract platforms may have their tokens designed to facilitate transactions. So if there's no transactions, then, there's no intrinsic value for the token, right? So that's one. Also, for Nervos CKB, for example, the native token is designed to capture the value of the assets. And that's the only way you can have a sustainable store of asset platform. Sometimes I give an example of, for a platform like Ethereum, if all the aggregate assets on Ethereum, the price go up 100 times, then there's no intrinsic reason that Ether will also follow that trend and go up in 100 times price, right? So in other words, the economic model for Ether does not provide a good value capture mechanism for the assets. But once you are a store of assets platform, you have to do that, right? So otherwise, you're going to be increasingly attacked. So those are the some of the thoughts that went into designing our platform. So again, it's it's a very secure and store of assets platform in the middle, and then there are a lot of transactional system around it. So if you guys are familiar with like a Polkadot or Ethereum 2.0. They all kind of have the similar topology, right? So something in the middle, and then you have a lot of satellite chains or parachains or shards. So we kind of have similar topology, but our insight is so the two things that can now coexist is a preservation-based economic protocol design, and the transaction-based economic protocol design, right? So this is why we feel like one layer should be about security of assets, and the other layer is about facility transactions. So I'm happy to talk more about this, but just want to see whether they're ready.
Thanks everybody for coming out. This is our monthly speaker event that we like to do. This month we have a couple of researchers from Nervos. We're going to talk about kind of different methods out there for scaling up Bitcoin. Obviously this is going to be a big issue going forward, but we'll have more information from them. So with that, did you want to introduce the speakers? Or I just call up Ren and we can go from there. All right, cool. Okay, so Ren's going to go ahead and start us off. We're going to do a joint Q&A at the end, so any questions you have, just kind of make a note of them or remember them, and we'll cover them together with both speakers. All right. Thank you, Ren.
I think just to clarify a little bit, our second speaker, Patrick, is not a researcher of Nervos. He's an assistant professor at UCL. Okay, good evening. NCMax is the consensus protocol of Nervos, a public permissionless blockchain. But this is just a temporary name. NC stands for Nakamoto Consensus, which is the consensus protocol of Bitcoin. If you have a good idea how it should be named, please feel free to come to me afterwards. My name is Ren Zhang. I'm a researcher at Nervos. And I'm also a PhD student of Bart Preneel of COSIC research group KU Leuven. If you're not familiar with COSIC, it's the birthplace of AES, the advanced encryption standard, which is used in all of your cell phones. And if you're not familiar with Bart Preneel, he's the designer of RIPE-MD 160, known in the Bitcoin space. RIPE-MD 160 is the hash function you use to compute from your Bitcoin public key to your Bitcoin address. So it's kind of... Nervos is a public blockchain that supports smart contract in all programming languages and has built-in support for all layer 2 protocols we're aware of. You can pay transaction fee in arbitrary asset, and it separates smart contract execution from verification for better privacy and better performance. Last but not least, it uses NCMax, a variant of Nakamoto consensus with higher throughput as its consensus protocol. So a disclaimer, this talk is only about layer 1 consensus protocols. I will not talk about sharding or Lightning Network. You can expect Patrick to tell you something about layer 2. So here's an outline of this presentation. First, I will tell you about why we love Nakamoto consensus and what we would like to change. Second is why we don't choose alternative consensus protocols. And last, I will introduce our own design. So why we love Bitcoin's Nakamoto consensus? We like it for its performance optimization. It is optimized to save every bit of transmission and every cycle of computation. For example, it uses compact block to accelerate block propagation. And it uses mini-sketch to save bandwidth for transaction propagation, hopefully in the future. And Bitcoin developers also develop GraphRoot. You can think of it as a compression. It's a way to compress Bitcoin's smart contract for better privacy and better performance. And hopefully we can see signature aggregation adopted in Bitcoin. We also like it for its generalizability. Its UTXO model plus global order of transactions allow support for all sharding and layer 2 solutions and complicated smart contract. In contrast, Ethereum's account model is very difficult to shard. And if you don't have a global order of transactions like many DEX, it is difficult to support complicated smart contracts. We like it for its security. Empirically, it is launched 10 years ago and survived many attacks. And formally, there is no known proof-of-work protocol that comprehensively outperforms Nakamoto consensus. If you're interested in more information about this topic, you can watch my talk tomorrow at Stanford Blockchain Conference at 10:30. There's a live stream. However, there are two things we would like to change in Nakamoto consensus. First, the protocol prescribes a manual throughput limit of 4 megabytes every 10 minutes. Although the bandwidth of Bitcoin public nodes has increased significantly in the past several years, there isn't a way to adjust the protocol to enjoy the increase of public nodes bandwidth. A natural question would be, just as indicated in this study, Bitcoin's IPv4 nodes, which used to be connected to the network with a median bandwidth of 32 megabits in 2016, have a median bandwidth of 56 megabits as of February 2017. A natural question would be, can the protocol itself dynamically adjust the throughput? A bad attempt of this approach is Bitcoin Unlimited. It hopes to increase the throughput dynamically, but instead, it introduces several new attacks that weakens the security of the protocol. By the way, I was the one conducting this research. The second thing we would like to change is its incentive issue, namely the infamous selfish mining attack. In this attack, the selfish miner withholds the discovered blocks, hoping to gain a larger lead on the blockchain, on the public network. And when other miner finds a block next, the selfish miner broadcasts the blocks to the network, the secret block to the network, hoping that the secret block will reach most of the compliant miners before the competing block. If the attacker is lucky enough, the next block is mined after the attacker block, the honest block is orphaned. If the attacker is lucky enough to find more than one block in a row, he can safely invalidate compliant miner's block because the attacker has a longer chain. And why is selfish mining profitable? Here's a concrete example. Assuming that the attacker's mining power alpha equals 30%, and honest miners control 70%. Without the attacker can find 3 blocks in 10, and the honest miner can find 7 in 10 on average. However, with the attacker finds 3 blocks in 7, and the honest miner finds 4 blocks in 7, because 3 of the honest blocks are orphaned by the attacker. And the main chain grows slower. In the next epoch, in the next difficulty adjustment period, the difficulty lowers because the main chain grows slower, and the attacker gets more reward with the same electricity consumption. That's why selfish mining is profitable. Selfish mining is not profitable in the first epoch of the attack. It is only profitable after the difficulty adjustment mechanism. And the difficulty lowers precisely because the main chain grows slower in the last epoch. Is that clear? This is a little bit technical. I was told to be slower when talking about technical stuff. Why we don't choose alternative consensus protocols? So, there are 3 approaches that doesn't use Nakamoto consensus or doesn't entirely adopt Nakamoto consensus. Proof of stake, DAG, and 2 block types. Note that these 3 approaches are not exclusive to each other. It's possible to adopt several of them. Let's take a deeper look at their security, functionality, and throughput. First, proof of stake. So all proof of stake protocols introduce some new security assumptions. For example, Algorand requires that most honest users can send messages that can be received by most other honest users within a known time bound, which means if you hold some Algorand token according to the original design, you have to be always online. If you are not online, you are not a valid token holder. And Ouroboros requires, which is used in the cryptocurrency Cardano, Ouroboros requires that all players have a weekly synchronized clocks, and all messages are delivered within Delta time. This is a very strong assumption, in case you didn't notice. There are numerous attacks to bias the clock of your mining gear, of your public nodes, of your cell phone. And this is very hard to realize in reality. And Sleepy protocol also requires players are equipped with roughly synchronized clocks. When these security assumptions are violated, which will result in catastrophic results in these proof-of-stake protocols. And it also introduced several new attacks that was previously doesn't exist in proof-of-work protocols. For example, nothing at stake attack, grinding attack, long-range attacks, and I'm not going to enumerate them. So what about DAG protocols? All DAGs has the transaction order problems. If you allow blocks to be produced simultaneously, then different miners or different public nodes will have inconsistent views on total transaction order. So I think these transactions are confirmed, while the others may consider a different set of transactions being confirmed. So at this stage, you have 2 options to solve that problem. Option 1 is you settle the transaction order after the blockchain topology is fixed, which means you have to wait a very long confirmation delay. Option 2 is that you leave the transaction undecided forever, which means some of the tokens are stuck in the smart contract or in the blockchain forever. Nobody can spend them anymore, which will limit the smart contract functionalities because some of the function call may be benign, but you lock the money anyway. And what about these protocols with 2 block types? Namely, they use a key block, which is similar to Nakamoto consensus block, to safely confirm transactions and use micro blocks, blocks that are broadcast between key blocks to increase the throughput. These protocols usually will have very long confirmation delay, similar to DAG protocols. In Bitcoin NG, the paper explicitly said that a user who requires high confidence will not gain better latency with Bitcoin NG, but must wait for several key blocks to accept the transaction as completed. In Bitcoin, they have a similar problem. So, what about their throughput? All these alternative consensus protocols claim to have very high throughput, right? Solana claims to be able to process 710,000 transactions per second. I think if you have a technological breakthrough like that, you deserve a Turing Award. So I can't wait for them to get the reward. And this protocol called NKN, they promise that they can have 10,000 nodes with 1 million transactions per second. For the record, I don't know how it works, but I'm really curious to learn about it. I'm also curious why Stellar and Ripple are Nakamoto consensus in their category. And I'm curious whether these 10,000 nodes are aware of this 1 million transactions per second. If you want to dream, you better dream big. This is a protocol that really dreams big. It claims to achieve 10 to the power of 12 transactions per second, and with a final confirmation time of under 1 second. I think the Earth is really not enough for them. They really need to find another planet who is big enough to deploy their protocol. So my point is self-claimed TPS are not comparable. Some of these TPS may be true, I don't know. But they're not comparable because they are simulated under different network conditions. Some of the simulations, they use network nodes of 1 gigabyte per second bandwidth. That is clearly not the reality. And they neglecting real-world factors. None of the simulations consider transaction synchronization. For them, the transactions are always already synchronized in their blocks. The purpose of the consensus protocol is only used to order these transactions, which is far from reality. And some simulations assume direct link between committee members, but in reality, every message is broadcast, because broadcast message will consume bandwidth of the public nodes. So here is our model for TPS comparison. We believe a public node's bandwidth is capped by 100%. You cannot go beyond 100%. And this bandwidth consists of 3 parts. The first part is the percentage of bandwidth used to synchronize transactions that are eventually confirmed. This is the real TPS, transactions per second. You need to first synchronize the transaction, then you can confirm them. The second part is the percentage of bandwidth wasted by the consensus protocol. The third part is the underutilized bandwidth. So the TPS is capped by 100%. And if you want to increase the TPS, there are only 2 things you can do. The first is you lower the consensus protocol's bandwidth consumption. The second is that you lower the underutilized bandwidth consumption. This is just these 2 things. You cannot do more than that. And you cannot go beyond 100% for layer 1 protocols. So let's look at this alternative consensus protocols bandwidth consumption. Many of them waste their bandwidth, waste their precious bandwidth on committee member communication. Algorand stores block certificate in order to prove to new users that the block was committed. So each block certificate is 300 kilobytes, independent of the block size. If you use 1 megabyte blocks, which means around 25% of bandwidth is forever wasted for synchronizing these certificates. So I was really wondering why they claim that their throughput is better than Nakamoto consensus. It doesn't make any sense. The second way to waste your bandwidth in consensus protocol is redundant transaction in the DAGs and orphan blocks. As indicated in this paper, if all the nodes in the DAG chooses the same subset of transactions for inclusion in their blocks, any 2 blocks that are created in parallel are likely to have many collisions, and throughput will not be high. Currently, all of the DAG protocols turn a blind eye on this situation. So the throughput is not satisfiable for us. So what's our opinion on this? So here's 3 major innovations of NCMax. To reduce orphans, we use 2-step transaction confirmation. To best utilize the bandwidth, we use dynamic block interval and block reward. To defend against selfish mining, we consider all blocks in the difficulty adjustment. Let me elaborate on that. So Nakamoto consensus has a natural throughput limit. Why is that? Because in Nakamoto consensus, if you want to raise the throughput, there are 2 things you can do. The first is that you increase the block size, as can be seen in Bitcoin Unlimited and Bitcoin Cash. I couldn't keep track of them. There are too many of them. And the second thing is that you lower the block interval. However, if you raise the block size or you lower the block interval, the orphan rate will increase. And these orphans, they consume bandwidth and they don't contribute to transaction confirmation. As your orphan rate increases, the security of the system goes down and the throughput goes down. So eventually there will be a balance in terms that the orphan is high enough that the throughput cannot go any higher, even if you try to lower the block size, try to lower the interval or increase the block size. So why are too many orphans bad for security and performance? As can be seen in this figure, when the orphan rate is very high, it's easier for the attacker to secretly generate a longer chain. The attacker doesn't need 51% of mining power. It can override the blockchain with much less mining power. And also these orphans, they can consume a lot of bandwidth of public nodes, which negatively affects the throughput of the system. So how do we break NC's throughput limit? If we want to break it, we need to lower the orphan rate. So if the orphan rate is lower, the security can be better and the throughput can be better. But how do we lower the orphan rate? The orphan rate comes from the block propagation delay. If during the propagation procedure of one block, another block is discovered, one of them is destined to be orphaned. So if blocks can be propagated instantly, there will be no orphans. So how can we make sure that the blocks are propagated fast enough, given that Bitcoin's developers already put a lot of effort in it to accelerate block propagation? We need to take a deeper look at where are some blocks propagated slower than the others. Some blocks propagated slower because these blocks have more fresh transactions. Fresh transactions are transactions that has been generated in 5 seconds ago or 10 seconds ago. These transactions are not synchronized in the network. So during the block propagations, miner will have to synchronize these transactions before they can further propagate the block. Let's take a deeper look how this happens. So in Nakamoto consensus, in the current implementation of Bitcoin, if everything goes well, a block will be very likely be propagated through a protocol called compact block. In compact block, transactions are not actually propagated as the entire transaction, which is 200 and 300 bytes. It is propagated as a truncated transaction ID, compact block ID. So this compact block ID, so these transactions, truncated transactions will compile the compact block. And this compact block is much smaller than an actual block. If when node A propagates this compact block to node B, and for node B there's no fresh transactions in it, node B can immediately transfer this compact block to all its neighbors, which is nice. However, when there are fresh transactions in the block, node B would have to first synchronize these fresh transactions from node A and then verify whether verify the signatures of these fresh transactions, which also takes time. And only when the validity of the entire block is validated can node B keep propagating this block. This is the main source of Bitcoin's block propagation delay. Is that clear? So Ethereum is a bad attempt. Let me tell you how they did it. So Ethereum simply shortened the block interval. But Ethereum has a problem that it is impossible to verify transaction validity before receiving the actual block, because the validity of a transaction depends on the order of the transaction within the block. So if you want to verify a transaction, you have to wait until the block is ready. So every block is fresh transaction. And this has poorly maintained network protocol. The network protocol of Ethereum has no update since 2015. And there are a lot of redundancy in transaction propagation. Ethereum client will propagate the same transaction 7 times to different nodes, which means for each node, he will receive the same transaction 7 times. And it has inconsistencies in different clients. The 2 main client implementation of Ethereum are basically separated from each other. So there are very few nodes that connect these 2 different networks. So Ethereum has a very high orphan rate of up to 30% sometimes, and very low transactions per second. And big miners have no incentive to accelerate block propagation, because if my block can be propagated slower, it means I can perform a de facto selfish mining, which is in favor of me. Why would I accelerate block propagation? And uncle reward surely doesn't help, because even if my block is orphaned, I can still get some reward. So small miners cope with this with header first block propagation and empty blocks. So I will not propagate the content of the entire block. I will just propagate the header, because it's so much faster. And because I don't know what transactions are included in the last block, I will man an empty blocks to make sure that my block will not contain a conflicting transaction with the previous block, which is bad because these empty blocks do not contribute to transaction confirmation. So how do we do it? This is the Bitcoin block format. We modify it by increasing several fields. First, we have a transaction proposal zone. This transaction proposal zone may contain some fresh transactions. And the traditional transaction confirmation zone can only contain transactions that was proposed several blocks before. For example, between 2 blocks before and 5 blocks before. Only these transactions can be confirmed. New transactions cannot be confirmed in the transaction confirmation zone. And the transaction proposal zone only contains truncated transaction IDs, namely the shorter version of the transaction ID. So the transaction proposal zone can be really small. And also, a block can include as many uncle blocks as you want. Uncle blocks should propagate their headers and their transaction proposal zone in the block. And uncle blocks don't count in block size limit, so that miners are not discouraged to include uncle blocks in their block. So let me give more detail about the transaction proposal zone. It is small because it only contains truncated transaction ID. And the complete transactions are synchronized after propagating the block. So they are synchronized in parallel. They will not affect the block propagation procedure. And it does not affect block validity as long as the hash checks. So which means in the transaction proposal zone, there may be invalid transactions, double spending transactions, and miners may refuse to provide some transactions in this zone. These are also fine. So recall that this is Bitcoin's block propagation. In our protocol, this is our compact block, which is slightly larger than Bitcoin's compact block. And compact block is always propagated immediately to your neighbors. And the newly proposed transactions, if some of them are missing in your transaction pool, they can be propagated after you send out the compact block. These two are parallel processes. They don't affect each other. And then these transactions are verified and propagated and to the next neighbor, and etc. Several natural questions. What if miners refuse to provide the complete version of proposed transactions? I put this transaction ID in my transaction proposal zone, but when you ask me, I don't know about it. It has no effect in block propagation because blocks are propagated regardless of whether there are fresh transactions in the transaction proposal zone. And other miners can still proceed with mining because there are enough proposed transactions to confirm. There's no need for miners to mine empty blocks because I know that there's a range of blocks that in this transaction proposal zones, the last block cannot include these transactions, which is only available for me. So I can mine these transactions, contribute to transaction confirmation. And what if miners incorporate this proposed without broadcast transaction in their later blocks to gain a de facto selfish mining advantage? In Nakamoto consensus, the advantage of slot propagation is always useful in finding the next block. For a miner, I can always, after I find a block, I only tell the block header and transfer the block really slowly. During this process, I'm the only one who can mine after this block. But in our protocol, it can only be used to slow down propagation unblock afterwards, because this propagated without broadcast transactions, only the selfish miner knows these transactions, and only the selfish miner can use it as an advantage. However, it cannot be used in the next block because there need to be a gap. A miner can only mine transactions that are proposed between 2 and 5 blocks. Before that, you cannot mine a transaction proposed in the previous block, as I said, but only if that block is found by the attacker. Here's an illustration. In Nakamoto consensus, when the selfish miner finds block H, it can immediately start mining the H+1 block. However, honest miner can only start mining after they receive the full block. And during the block propagation period, that's the selfish miner's advantage. However, in our protocol, when the selfish miner finds block H, honest miner can immediately start mining H+1. And if the selfish miner wants to utilize this proposed without broadcast transactions, it has to find the block, unblock afterwards. Only then can the selfish miner utilize this advantage. However, this happens less often. You cannot be sure that after 7 blocks, there will be a block mined by me. It's very hard to predict that. So to best utilize bandwidth, our protocol uses a different difficulty adjustment mechanism, which targets a fixed orphan rate, counted as uncles in the last difficulty adjustment period. If the orphan rate in the last difficulty adjustment period is below the target orphan rate, the difficulty will lower, and the block interval will lower, and the throughput would increase. In other words, that very few orphans means the network can synchronize transactions faster, which means we can increase the throughput without harming the without harming the decentralization, whatever. Otherwise, the difficulty increase and the block interval would also increase and the throughput will decrease. A higher orphan rate means the network cannot process this much transactions in the difficulty adjustment period. Then we can lower the throughput. And the block reward is proportional to the inverse of the expected block interval, so that the expected total reward per difficulty adjustment period is fixed, which means if you have 10 minutes per block, and each block has 12.5 Bitcoin, when you have 5 minutes per block, each block can have 6.125 Bitcoin. So the issue rate of the currency is always fixed. Last, to defend against selfish mining. So recall that, the difference between our protocol and Nakamoto consensus is that difficulty adjustment mechanism counts all blocks, including uncles, when estimating the total mining power. Same as Nakamoto consensus, without the attacker finds 3 blocks in 10, the honest miner finds 7. With the attacker finds 3 blocks in 7, and the honest miner finds 4. 3 of the honest blocks are orphaned, and the main chain grows slower. But recall that selfish mining is not profitable in the first difficulty adjustment period. What happens in the second difficulty adjustment period? In the next epoch, the difficulty will stay the same, and the attacker cannot find more blocks with the same mining power. Therefore, selfish mining is no longer profitable. Is that clear? So in sum, our protocol makes use of orphan blocks. These are a symbol of orphan blocks. We want to reduce the number of orphans by 2-step transaction confirmation. And after the orphan is reduced, we use the remaining ones as an indicator of bandwidth utilization to adjust the throughput. And given that on-call information is embedded in the blockchain already, we can use them to make selfish mining unprofitable. That will be all. Thank you.
Thank you, Ren. Less orphans in the world is a nice goal. Why don't we just go ahead and bring on Patrick up, and we'll do his talk next, and then we'll have a joint Q&A after.
Hi guys, so my name's Patrick McCorry. I'm a professor at King's College London. And today I'm going to talk about, I guess, the brief I was given was how could we improve payment channels in Bitcoin. So a lot of my research for the past 2 years has mostly been on Ethereum. So that's why my research is sponsored by the Ethereum Foundation and the Ethereum Community Fund. And I'm hopefully going to show you why a lot of my research has been there recently. Because trying to design protocols in Bitcoin, it's not very easy to do. It's a bit awkward. You sort of fight in Bitcoin in the submission to get it to work. So my thoughts are, how can we stop that? How can we actually change Bitcoin a little bit such that building payment channels is a bit more straightforward? But before we get into that, my clicker's not working. I'll just do this. Okay. Why do we need, payment channels? So raise your hand if you're excited for the Lightning Network. Who's excited for it? We're all excited. There's one person there who's not excited. But yeah, we're all excited for the Lightning Network, and that's because cryptocurrencies do not scale. Bitcoin supports, 7, 10 transactions per second. Ethereum supports, 10 transactions per second, but that's a bit of a misnomer, because one transaction could fill an entire block. And the question is, why do they not scale? Why can't we achieve 5,000 transactions per second? And I sort of this guess runs off Ren's talk as well. For me, at the heart of the scaling dilemma is public verifiability and holding the miners accountable. What do I mean by this? So in the Bitcoin world, we have 1, 2 megabyte blocks now. That's a really old slide. I should oh, that was an old slide. This isn't. Okay, but the point is, the blockchain's about 190 gigabytes. I can download this on Ren's laptop. I can still validate every single transaction that's ever occurred, catch up to the entire network, and now I can hold miners accountable for every new block they produce. But we actually harm the diversity of peers who can use the network. Because as we've seen at Christmas 2017, the fees went from 20 cents to $20. And raise your hand if you're going to pay $20 for a Bitcoin transaction. Okay, no one. Okay, one person. Oh, 2, sort of. He's sort of like, sort of. But that's the point. I mean, by restricting the block size, we actually restrict the number of people who will use the network. But on the other extreme, if we have 1 gigabyte blocks and we do 5,000 transactions per second, we'd like to think transaction fees would be lower. So anybody could afford to use the network. But on the flip side, we will actually reduce the diversity of peers who can hold the miners accountable. Because this laptop definitely cannot verify 5,000 transactions per second. It doesn't have the bandwidth, the computational resources, or even just the storage. So by doing that, only very select few people can actually hold the miners accountable. So the question is, with that in the back of our mind, how can we scale these cryptocurrencies? The first approach is you could say, screw it, we don't care. Let's have a central authority. They sign blocks and they just pump them out. But we're cypherpunks. We don't want that. We don't want any weird central authority. We're trying to get away from that. That's the beauty of cryptocurrencies. The second approach was, I guess, Ren was talking about, we can tweak the consensus protocol. We can tweak the blockchain protocol. We can do what maybe Thunder's doing or Definity or throw a DAG in there. And let's pretend we could achieve 5,000 transactions per second. We then run into that public verifiability problem, where we can no longer hold the miners accountable. So that's not going to work for what we want to do, at least in my mind. The next approach people are thinking of, and this is very much ETH 2.0, their whole hope is on sharding. And sharding is a really basic idea. There's a shard for hotel bookings and a shard for train bookings. If I only care about hotel bookings, I just validate this one shard, and I forget about the other transactions. If I care about train bookings, I only validate the shard for train bookings. So I can distribute out the task of validation. But in the worst case scenario, you still have to validate every transaction if you care about hotel bookings and train bookings, or if you just care about cross-shard communication. So we can distribute out the task, but we never get rid of that validation problem. So that's why I'm quite interested, or I guess bullish if you want to say, in off-chain. Because the whole point of off-chain is that we don't increase the network's throughput. We don't increase the bottom layer. We still only have 7 transactions per second. But what we do is reduce the load. 2 parties can lock up coins, and then they can transact locally between themselves. And they never have to interact with the global network. And at the very end, they send 1 transaction that represents their final balance. So they can do thousands of transactions for free, locally, without interacting with the global network. So we just reduce the load. That is how this scales the network. But I think that's really exciting. Now the question is, what is a channel? What is the definition of a channel? So in the summer, I hosted this workshop in Berlin called Master Workshop about Layer 2 solutions. And what I did was that I invited 7 different teams who all work on payment channels, Lightning, state channels. And they came, they gave presentation after presentation. What I learned is that every single team has different terminology and different definitions. So there's a whole language barrier between different teams over this very basic idea. So what I'm going to give you guys is my definition of a channel or a state channel. The idea is the following. There's a group of parties, and they basically want to run a smart contract or do some transactions. And all they want to do is collectively agree the new state of a program. So let's just say we're playing poker. I play my hand, and the new state of the game is that I've played my hand. Everyone will agree and sign the new state update to say, the new state of the game is that I've played my hand. If this is the payment channel world, Alice pays Bob, both parties authorize that, and the new state of the balance is that Alice has paid Bob. That's the basic concept of a channel. But what they should give us is 2 guarantees, or at least we normally assume the underlying blockchain gives us 2 guarantees. One is safety. If I have 10 coins in the channel, I should always be able to get my 10 coins back. I should always get the coins I deserve. The second property is liveness. What if we're playing poker off-chain? Alice plays her hand, she's just about to beat Bob. Why would Bob ever sign that state update? If he signs it, he loses the game and he gives away $100. So in the worst case scenario, it should also guarantee liveness, that the application will always progress. I just trigger a dispute on the blockchain, I say this is the latest state, I redeploy the poker game, and I just finish the poker game on the blockchain. And this is the same for payment channels. So if you guys consider a conditional transfer, like in Lightning, I say, you can claim these coins if you reveal the pre-image of a hash. That is a liveness requirement. I should always be able to redeem the conditional transfer on the blockchain as a one-step state transition. But that's basically the idea of a channel. Now, in the Bitcoin world, there's 3 different channels. There's Spielman channels, duplex payment channels, and Lightning channels. And what I'm going to do, hopefully for the next 10 minutes, is go through each channel construction to really highlight the progress from 2013 to 2015 in the payment channel world. So let's talk about Spielman channels. Who's heard of Spielman channels, by the way? Raise your hand if you've heard of them. Spielman channels are basically one-way payment channels. In this case, Alice can pay Bob, but Bob can't pay Alice. So what Alice will do is deposit coins into the payment channel. So we call this the funding transaction. And these coins can be redeemed if one of the following 2 conditions is satisfied. Alice can get her coins back after time t. The channel expires, she's refunded, she gets her coins back. The other condition is that, I should say Alice and Bob. Okay. So the second condition is that if Alice and Bob both agree, they can close the channel at any time. And that's normally done before time t, because otherwise Alice gets refunded. Okay, so the first one is that Alice gets her coins back after time t. The second condition is supposed to say Alice and Bob must agree to release the coins before time t. Okay, so the first payment is where Alice will create a Bitcoin transaction. So in this payment channel, there's 1 coin. There's 1 Bitcoin. And that's owned by Alice. Now, Alice creates a Bitcoin transaction, and she wants to pay Bob 0.1 Bitcoin. How does she do this? She creates this transaction where she simply redistributes the deposit. Alice is going to get back 0.9, and Bob's going to get 0.1. She signs it, and she gives it to Bob. And now Bob can make one of two decisions. Bob could sign it, broadcast it to the network, and immediately redeem his 0.1 Bitcoin. But he's aware that Alice can't get these coins back until time t. So let's pretend we could say Alice doesn't get refunded for 10 days. So Bob could just wait around. He's like, well, as long as I claim this within 10 days, I'll always get my 0.1 Bitcoin. So he just keeps it private for a bit. And then, bam, there's another payment. Alice creates a second Bitcoin transaction where she wants to send Bob 0.5 Bitcoin. How does she do that? She gives herself back 0.4, and she gives Bob 0.6. She signs this, passes this to Bob, and again, Bob can just make the exact same decision. He just keeps it private for a while. And then finally, as you can sort of guess, oh, I didn't update that part of the slide. Okay, I didn't. Anyway, so the whole point here is that there should only be one output. Alice signed a transaction. So he wants to send Bob the final 0.4 Bitcoin. So in this case, Bob's going to get a transaction with one output where he receives the entire Bitcoin. Okay? So Alice has now sent Bob one full Bitcoin in the payment channel. Now, because this is a one-way payment channel, Bob can't pay Alice. So the only option is now to close the channel. So Bob gets the most recent transaction he received that will pay him the most money, which is one coin in this case. He signs it, and he broadcasts that to the network. And that's basically called replace by incentive. That's the whole point of a Spielman channel. We set up the channel, I keep sending updates to Bob, and I'm basically replacing the state every time I sign a new transaction. And Bob's only going to broadcast the one that pays him the most money, and that's his incentive. So that's what we mean by replace by incentive. Is that clear to everyone, by the way? Cool. Because I made these very quickly, so I want to make sure it's all sort of clear. Cool. So the next question is, how do we achieve bidirectional channels? Alice can pay Bob, and Bob can pay Alice. So this gets to sort of 2014, I believe, replaced by time lock. Okay? So the idea is that the channel is again locked up for a certain period of time. Maybe 20 days, let's say. So Alice deposits one coin, and Alice is guaranteed to get these coins back after 20 days. Okay? And now every time we change payment direction, so when Alice pays Bob, and then Bob pays Alice, we're simply going to decrement that time lock. And I'm going to show you how that works. Okay? Yeah, so I'm just going to move on from that slide. Okay, so the funding transaction will say the following. Alice is going to create a Bitcoin transaction, broadcast it to the network, and she's going to lock one coin into this channel. And it can only be redeemed if Alice is refunded after 20 days, or both Alice and Bob agree that the coin can be spent. Very similar to the before. Now, when Alice pays Bob 0.1 Bitcoin, this payment transaction is going to decrement the lock time. So now Bob can claim this coin after 19 days, but he must claim it before 20 days. Okay? So that transaction is only valid after 19 days. Okay, so is this clear to everyone? Okay, so that's valid after 19 days. The funding one is 20 days. So Bob has 1 day period to claim the coins. Okay, and Alice could keep sending updates. So we can use replace by incentive here as well. As long as Alice is paying Bob, that time lock never needs to decrease. But when Bob wants to pay Alice, Bob will create a payment transaction, he'll sign it, he'll give this over to Alice, and in this case, he's going to send back the entire 0.3 Bitcoin that he received. But when Bob does this, we decrement the lock time to 18 days. And why do we do this? Because Bob must have in this case, Alice must ensure you know, if she's going to start receiving coins from Bob, that she can always broadcast this before Bob can broadcast the payment he received earlier. So that should roughly be clear. It's a bit hard to understand when you first look at it. But that's the basic idea what's going on. But the problem there is that every time we change payment direction, this time lock comes closer to the present time. So that limits the throughput. You know, if we keep changing directions lots, we're just going to end up, you know, closing the channel because we have 1 day left or a couple of hours. So Christian Decker had this proposal called duplex micropayment channels, where he tries to combine the best of both worlds. Replaced by incentive, that was the first proposal, and replaced by time lock. Okay? And the way he does this is the following, and we're going to look into both components. The first is a pair of one-way payment channels. There's a one-way payment channel from Alice to Bob, and another one-way payment channel from Bob to Alice. You know, if Alice wants to pay Bob, she does in this one-way payment channel. If Bob wants to pay Alice, they do it in this one-way payment channel. Now, when they run out of coins, the idea is that we'll be able to destroy the pair of one-way payment channels and then recreate the one-way payment channels again, all off-chain. So we can just reset those one-way payment channels. And we do this using this quirky invalidation tree. And that relies on replaced by time lock. So let's look into that a bit. This is basically what the pair of one-way payment channels look like. Okay, there's some transaction that they're, you know, relying on, and then Alice can pay Bob there, and Bob can pay Alice there as well. So that should be roughly clear what's going on. And if it's not, you're going to understand why I hate payment channels in Bitcoin, because this is overly complex for what they're trying to do. So anyway, and then once those one-way channels run out of coins, you know, so there, you know, let's say Alice has sent all her coins to Bob, and in this transaction, Bob has sent all of his coins to Alice. Once we've run out of, you know, capacity or coins available to send, we have to destroy these one-way payment channels and recreate them. And we do this using this quirky invalidation tree. So if you look over there, there's this invalidation tree where there's a funding transaction, then there's 3 transactions in the middle with different time locks. And then at the end, you have the pair of one-way payment channels. So if you look at the very top, you know, the second branch can always be broadcast before the first branch. Because down there, the very first transaction is followed by 99 days, where the other branch at the top is followed by 100 days. So every time we destroy these pair of one-way channels, we create a new branch in the tree. And the one going this direction is always valid first. Is that roughly clear what's going on? I know it's very quirky. That's why it's never really been built. But that was the state of the art in 2014. And that's really important. Okay, this is all very clunky. You know, it's not very straightforward to understand. And what you notice is that, you know, it's actually, the whole point of this invalidation tree is that every time we destroy the one-way payment channels, we still have to decrement the lock time. You know, we still get closer to the present time. But we sort of try to delay that a bit, so it's not as bad as it used to be. That's the whole point of that invalidation tree. So they're trying to, you know, reduce the limit on the throughput and try to ease getting rid of that expiry time. So what was really exciting about the Lightning channels is that Lightning fixed that. Lightning has no expiry time, and there's no real limit on the throughput either. But that doesn't come for free in the Bitcoin world. Okay? So Lightning is the following. Both parties must always cooperate in every single new payment. So let's pretend for now that the state is just the balance of both parties. You know, Alice's balance and Bob's balance. Now to do a payment, we do the following. We both agree the new state of the channel. So if Alice is paying coins to Bob, let's just say Alice sends 1 coin to Bob, the new state of the channel may be that Bob has 1 coin and Alice has 0 coins. So both parties agree the new state. And after they've agreed the new state, they revoke the old state. Okay? So now there's one valid state that should be broadcast to the blockchain, and the previous one is invalid and should never be broadcast. And this keeps happening. So every time we do a new payment, we always authorize the new state first, and then we revoke the old state. So it's like a two-phase commit, if you're familiar with that. Now, in the Lightning world, the state is a pair of transactions. Alice has a transaction that she can always broadcast, and Bob has a transaction that he can always broadcast as well. So the state is just two transactions that either party can broadcast at any time. And I'm not going to show the transactions because it doesn't really fit on a slide very well. I do have slides for it, so I could get it up later, but it's overly complex for the slides. But anyway, the next question is, what happens if you broadcast an old state? You know, what if I broadcast state 8, for example? Maybe if I broadcast state 8, I can reverse a payment. You know, Alice has 1 coin in state 8, but now in the current state says 0 coins. So Alice wants to broadcast the old state, because if she does, she could get her 1 coin back. So what happens is that, okay, in this case it's state 4. I want to move my mouse. How do you get rid of that? Okay, gone. You know, Alice broadcasts state 4. Now, what's really cool about Lightning is that it now triggers this dispute process. And to the best of my knowledge, it introduced this idea of a dispute process. Who's familiar with the idea of dispute processes, by the way? Some people are. So the whole point here is that once we trigger a dispute on the blockchain, there's now a fixed time period. So let's just pretend Alice triggers the dispute. There's now a fixed time period for Bob to submit evidence that Alice is cheating. If the dispute process expires, this is considered the final state, and Alice will get the coins according to that state. Okay? So in the Bitcoin world, what Bob would have to do is broadcast a justice transaction. They've renamed it in 2 years. It was called something else before. But they call it a justice transaction now, which is really fancy. So the idea here is that Bob basically submits a transaction where he can prove that state 4 was invalid. If Bob can do that, then what happens in Lightning is that Bob will get all coins in the channel. So Alice gets punished. Okay? So just to recap, let's pretend state 4, Alice is trying to get her 1 coin back. So he sends his older state where she has her coin still. You know, he's trying to reverse a payment. Bob will send the justice transaction that will prove that state 4 was invalid. Once the blockchain is convinced that state 4 is invalid, Bob will get all coins in the channel, which would be 1 coin in this case. So Alice will forfeit her entire balance. Now, what do we need to create a justice transaction? Typically, a party needs to keep a pre-image, a secret. So what happens is that every time we authorize a new state, we agree to a new pair of hashes. And then when we revoke an old state, we just exchange the pre-images. So if you broadcast state 4, all I need to do is show the blockchain the pre-image or the secret of a hash, and that's sufficient to prove that it was revoked. So that's basically what's going on there. If I can prove to the blockchain I know the secret, then this must be revoked. Now, the issue is that for watchtowers, they can't hold around this pre-image. Because of the way the Bitcoin script works, the watchtower actually has to hold a pre-signed justice transaction. They can't sign a transaction on behalf of another party. And that's really problematic. So who's heard of Watchtower before? Some people have. So this is why Watchtower doesn't work on Bitcoin right now. Because they have to hold around this justice transaction, they have to hold around a pre-signed transaction for every single revoked state in the channel. So if we do 1,000 payments in Lightning, the Watchtower will have to store 1,000 justice transactions. And that frustrates everyone, including the Lightning developers. You know, that's something that should be fixed. And there's ways to fix it. But that's basically the high-level view of how Lightning channels work. You know, replaced by revoke. Was that clear to everyone? Is there any questions? So I know this is quite technical. Okay, we can take it afterwards. Cool. Anyway, so this is sort of the lesson. So I was working on this in 2015. I learned how all these worked. And, I mean, it's really exciting to see something like Lightning work today. So basically, when you use LND or C Lightning, that's what's going on under the hood. So what's really cool is programmed, is deployed today. But what we learn is that over the period of 2 years, you know, we had this replaced by incentive, replaced by time lock, and replaced by revocation. But every time we solved the problem, you know, removing expiry time, increasing the throughput, the protocols just got really clunky and awkward. So awkward that I'm not going to show the Bitcoin script on the slide. You know, so concretely, what problems actually emerge? So these are all my thoughts at the moment. This isn't written down anywhere. I do want to write it at some point. It's on my to-do list. So these talks are really useful because it makes me sort of concretely in my head understand what's going on. Really the problem is that the state, you know, that balance, you know, Bob's balance and Alice's balance, it's intertwined with the transaction. You know, and that sounds awkward, and that'll be clear very soon. They should be separate. I should have a transaction, and I can get my state and put it in the transaction's payload, and the transaction just delivers a message. It should not be intertwined with the state. Watchtowers are not yet practical because the state and the transaction are intertwined. If they weren't intertwined, I could just send all the pre-images to these watchtowers, and they could just broadcast one of the pre-images, and then prove it was revoked. They don't need my signature to do that. And transaction malleability was a pain in the ass. Who's heard of a transaction malleability before? Yes, some people have. You should read this paper, by the way. It's really awesome. Mt. Gox tried to blame, everyone knows about Mt. Gox, I guess. They lost 850,000 Bitcoin. They tried to blame it on transaction malleability. Christian Decker did network, you know, measurement, and he provided evidence that, you know, they were talking shit. You know, they really didn't lose it because of that. But because of transaction malleability, Lightning could not operate on Bitcoin until 2017, until SegWit was implemented. Because SegWit fixes the transaction malleability problem. And of course, if the state was, and actually this is fundamentally because the state and the transaction were intertwined. If the state was separate from the transaction, we would never need SegWit. You know, transaction malleability would just not be a problem. But of course, here it is. What's also really frustrating is that in Lightning, or in Bitcoin, sorry, UTXO, the way it's implemented today, only supports a single state transition. You know, I spend an output, and I create another output. The input cannot control how the output is created. If you use something like Covenant, that was by Malte Moser, that would fix that problem. Now, why is this a problem? Okay, in the Lightning world, it's because once we trigger that dispute, you know, once I broadcast this transaction, I send this revoked state, there's now only one piece of evidence that can be sent. It's only one state I can send. Okay? So the deal with this, Lightning has to punish the counterparty. If I send this older state, I always get punished because there's no other way really to recover from that situation. And replaced by time lock, this is also the reason why we can only broadcast the transaction just in time, you know, between 18 days and 19 days. There's no way to update the blockchain within the dispute period to say, wait, there actually really was a valid state, you know, a new valid state. We have to rely on time locks to try and enforce the right period for the valid state to get in, or we just punish the counterparty for sending an invalid state. And, oh, did this slide not update? It did update. And Lightning makes sure your node doesn't crash either. I'm sure some people have seen this Reddit before. But it's really important because in Lightning, if I lose the latest state that was authorized, my database now only has revoked states. So I have two options, you know. I broadcast it, I get punished, or I ask the counterparty for it and they tell me to go away. Because now they're guaranteed all the coins in the channel. So if I lose the latest state, I'm basically in a really awkward situation where I can't do anything about it. So that's a practical problem in Lightning. And the protocol, there's no way to fix that yet. So this is how I normally feel when people tell me about channels in Bitcoin. It's just really constrained. You know, it's the way it's not done on purpose. You know, Satoshi Nakamoto never envisioned like how Lightning would work or payment channels would work. He had an idea for payment channels, but he didn't have the protocol in mind. So Bitcoin was never developed with that in mind. So it's really awkward and constrained trying to build anything on it. It's really stressful. So this is why I've been doing a lot of Ethereum stuff recently. And whether you love or hate Ethereum, what I'm going to hopefully try to convince you guys today, it helps us build simpler protocols. You know, Ethereum still has its problems, has lots of problems. But abstractly, the idea of these smart contracts are really good for protocol design. They're not really good for dApps. They're better for designing protocols. So we have write-in channels, which I'm not going to explain now. That's another way to do payment channels. What I'm more interested in is this idea of a state channel, where instead of just payments, you know, we could actually just take a smart contract and locally execute it between a group of parties. You know, we can do gaming, voting, auctions. And what's really exciting is that we can basically run the smart contract for free. You know, if we have a state channel, there's no miner to reward, and there's no hub to reward either. It's a group of parties. It's like a LAN party back in the 90s. You know, you bring your desktop computers and you play games. We all come together and we just run it locally between ourselves. But what's really exciting about state channels is that the way the channel construction is, it's really straightforward. Okay? So this is Kitsune, which we were designing last year. So the idea is that the state of the channel is basically, you know, a signature from each party. It's a hash. You know, we just hash the state, which could be, you know, the balance of both parties in some random nonce, and a counter. So whatever message has the largest counter is considered the most recently agreed state off-chain. If that's counter 100, and I broadcast 99, you know, 100 beats 99 is always the latest state. So we call this replaced by version, you know. So whatever state off-chain has the largest counter is always considered the latest state. And the dispute process is really straightforward as well. One party can trigger a dispute. Now there's this fixed time period for anyone to submit, you know, the latest state hash with the largest counter. Now what's really nice is, because it can store some state and is somewhat expressive, we can actually, you know, just submit as many states as we want. So we send multiple states, and when we resolve the dispute, we'll always accept the state with the largest counter. And it's very easy to build a smart contract that will do that. So this is really exciting. It's a real good playground for designing protocols. And after the dispute is resolved, you know, you could just redeploy the app and finish it there. So this could be a payment app. You know, there's a pay function, a withdraw function. We redeploy the app and we just call the withdraw function. You know, it's fairly straightforward. They're just programs. There's no expiry time. You know, there's relative time locks. There's no transaction throughput limitation. We don't sign transactions. We sign a commitment to the state. And there's no clunkiness. It really is just really straightforward to do. And this isn't new to Bitcoiners either. You know, what I'm presenting here is not like, you know, outrageous thoughts that might anger people. This is well accepted by Bitcoiners in this space. So sake hash no input, and L2 is actually designed to do replace by version. So L2 is by like Rosa Beef and Rusty and Christian Decker. And this is a diagram from their paper. But the whole idea is that, you know, we can trigger a dispute, and then the blockchain have this dispute period where we send, you know, the latest output. Eventually that one gets accepted, the dispute process is over, and then we just send the coins off whatever way they want. And this is all based on hashes and counters. So they've actually sat there and thought, well, actually, state channels are really cool. And their design is really simple. So how can we get this to work in Bitcoin? So this is sort of the direction that they're going now. And whether, you know, actually I should mention, on Monday we were at dinner, and Rosa Beef and someone else made a bet. You know, whether say cash, no input, we'll get into Bitcoin by the end of 2020. You know, someone betted against it, Rosa B betted for it. Actually, what do you guys think? You know, raise your hand if you think say cash, no input will get into Bitcoin by the end of 2020. 1, 2. And raise your hand if you have no idea what I'm talking about. Oh, everyone does. Okay, so you're optimistic. That's up. I mean, I'm sure I would like it to get in. I don't know if it will, but this is good though. You know, the people working on these protocols, they notice how clunky Lightning is, and they want to fix it. But Bitcoin, we can't do that yet. We need these new consensus rules. So if you do see a proposal for say cash no input, please push for it. You know, make their job easier. So my guess one takeaway here is, even if you don't like Ethereum, you know, not many me, people always have their opinions. The biggest lesson for me was that it's much easier to design protocols. You know, that dispute process I could write in about 20, 30 minutes. You know, one joke in academia is that I designed a protocol for Bitcoin, I get a top-tier academic conference. I design the same, you know, protocol for Ethereum, and I get a blog post. You know, because the complexity is just completely different. In case of this dispute process, when you really think about what's going on, you know, the blockchain is just a trusted third party. You know, we trust it to control this dispute process. And in this case, you know, it's to work out the final balance of both parties and throw it away and send off the coins. So smart contracts are not about dApps. Not really. You know, the goal of decentralization is not the right goal. What we're actually doing is building these third parties that are verifiable, they're accountable, and they self-enforce the protocol's execution. All they solve is coordination. If I want an auction, I need an auctioneer. The smart contract's my auctioneer. They control the auction process for us. They don't really do anything exciting. There's just these third parties that just run the protocol for us and make sure we all are well behaved. And at the root of it, it's just essential for any fair exchange protocol. And that's what off-chain's about. Being able to trade coins in a way that's fair. And nobody can cheat. So thank you for listening to this talk. I don't know if that was 30 minutes or not. I have no idea. But I haven't done this talk before. Yeah, well, let me finish this one part of the slide. So I do a lot of my work with these guys over here. So that's Sarah Meiklejohn, Ido Bentov, Chris Buckland, Sarah Bakshi, Andrew Miller. And without these guys, none of this work would really be here. You know, they sort of deal with my rants half of the time. So I first started in this with Sprites, and that was by Andrew, where Sprites has like two components. One is this pre-image manager that reduces the worst time case in Lightning. Makes sure you have like a constant time lock. But another aspect of the paper is that it actually has one of the first state channel constructions. Like, how do you build a state channel? How do you do replace by version? And that's always never really noticed in the paper. And then we built Pisa. So Pisa is sort of like Watchtower. It's an accountable third party who can watch the channel on behalf of others. And the whole point of Pisa is that it's accountable. You have evidence, you've hired the Watchtower, and if the Watchtower cheats, you can also punish the Watchtower. That's basically what Pisa contributes. We also built a Battleship game for Kitsune. So in the summer, you know, state channels, we know how to build state channels, but they're eluding real world use. So we built Battleship to say, you know, do state channels actually work? You know, can we play Battleship? Can we play chess, and do they scale out? And I can talk about that during the Q&A if you want. They don't scale out at all, and Battleship doesn't work, unfortunately. And I can talk about that. That was my talk earlier today. And finally, we released this new paper. I just put it online today. It's just a short paper of like 8 pages. But one problem with these state channels, so if you're running a program, like auctions or voting, when you trigger this dispute, you have to send the entire state. If you have to send the entire state of like a Battleship game, that's quite a lot of information to send to the blockchain. So this protocol pretty much allows you to only send a hash. An honest party will always get refunded if they have to send the full game state. So it's a constant cost dispute process. It has its caveats. You know, it's not too general yet, but it does work. But that's it, I guess. That's the end of my talk. So thank you guys for listening.
Thank you.
Awesome.
Why don't you go ahead and bring our first speaker back up, Ren?
Yeah, where's
Ren at? Oh, yeah. Why don't you come on up, pull these chairs for a little bit, and If I can ask you two to share the microphone, I'm going to walk around the audience with this mic, and if you have the mic, you can talk. If you don't have the mic, you can't. All right, here we go.
Awesome. Thanks, man. Hey, good talks to you guys. Really interesting. Question for Ren. What are the implications of the proposal transactions? Like, I'm having trouble wrapping my head around, because essentially you're broadcasting the mempool with the transaction block. And so it seems like that's an incredibly inefficient way to do it, is to actually have the block consume the mempool functions. But obviously that's not exactly right. I mean, there's more nuance there. But like, what are the other implications of having the proposal transactions built into the compact block, besides larger blocks are getting pushed out?
And I think your question is, what are the trade-offs? What are the pros and cons? I think the cons is quite obvious. Is that because you cannot confirm transactions that is fresh or in the previous block, there has to be at least 2 blocks before that, which means transaction confirmation usually takes longer block intervals. So for Bitcoin, if consider the same level of security, if in Bitcoin it takes 6 blocks to confirm a transaction, with the same level of security, in our protocol, it takes 8 blocks. These are the cons. But the pros is, having this transaction proposal zone allows us to shorten the block interval. So the 8 block confirmation within our protocol could be faster than the 6 blocks confirmation in the traditional Nakamoto consensus protocol by just modifying the block interval.
How much larger are the blocks?
I need to ask the developers. The detailed parameters are not fixed yet, but it should be relatively small. Yeah. The additional part, the transaction proposal zone and the uncle zone should be all relatively small. It shouldn't be larger than the traditional, or it should be significantly larger than the traditional compact block.
Yeah.
This question over here.
Yeah. I thoroughly enjoyed both of you guys' presentations. But my question is to Ren. There was a part where you said about, I think it was about the selfish mining portion, where you said there's enough transactions for confirmation, so there's no reason to send empty blocks or something of that nature. And my question was like, what about if there's a case where where there's a period where new transactions aren't occurring? How does that affect that part of the assumption? Or was I misunderstanding what you were conveying when you were saying there's always enough? Because I know it's the delayed transactions that you're confirming, but then after those are confirmed, if no new transactions are occurring, then you would have empty blocks, right?
Sorry, I didn't quite get your question.
In your presentation, there was a specific slide you said
but there are enough transactions to be confirmed.
Yeah, you said there's enough transactions to be confirmed. So where are those? If people aren't making transactions, where are those transactions coming from?
In Bitcoin network, the transactions are broadcast to the entire network. So if you want to make a transaction, you just construct the transaction on your phone, on your Bitcoin wallet, and you broadcast it to the Bitcoin network. There are around 10,000 nodes, I think. And eventually, these transactions will be broadcast to the miners, which you'll consider including your transaction in the blockchain.
Okay.
So who decides, like the thing I'm thinking about is like you have low or zero fee transactions.
These transactions are called dust transactions. If the transaction fee is too low, it will not be propagated in the network.
And so I will make a decision not to push it into the transaction proposal. But essentially what you're giving, that's right?
But I think it's so including transaction in the transaction proposal zone, it's I'm considering a reward, an incentive mechanism that 40% of the transaction fee goes to the miner who first put this transaction in the transaction proposal zone, and the other 60% goes to the miner who actually confirmed this transaction. But this is like a little controversial in the Bitcoin space, so I still haven't decided whether I will implement this fee mechanism yet.
Question to Patrick. Have you run simulations for state channel to account for like a flood attack where folks are just broadcasting, pretending that there's a dispute or whatnot, just to flood the network and trace what the true cost is on the network, not necessarily just the fees?
Let me see if I understand that. So you have this dispute process, and you're saying that the counterparty is flooding it with lots of updates. If I'm an honest party, I just send the latest state. So I only need to do one state update, and then you can't flood it anymore. Because if you think about it, if I'm an honest party, I trigger a dispute, and I say, the latest state of the game is counter 100. You can't broadcast another state then, because that's the latest state. If that's your question.
Perhaps the channels themselves, they are attacked, so there isn't like an innocent one in that channel where they're just designed specifically to flood the network, where they, each and every one of them, they keep issuing disputes.
I think there's a related problem there that's probably better. What happens with network congestion? Is that what you're alluding to? The network's congested and I just can't even trigger a dispute. Is that like sort of...
Exactly.
Okay, that's awesome then, okay. So I've had thoughts around this. So all channels today, if there is congestion, one, maybe my transactions just can't get in because it's too full. Maybe the transaction fee is too high, and it's no longer economically viable for me to actually send the evidence to the blockchain. What I'd really like to see is this new opcode, where we could self-inspect blockchain congestion. So instead of saying that the dispute process expires by time t, we could say, well, let's look at the previous 2,000 blocks, where 500 blocks reasonable to get into. If they're reasonable, then we can finish the dispute process. So then we could self-inspect for congestion, and then, if the network's congested, we just ignore those blocks for the dispute process. But that's a work in progress. There's no proposal for that yet. Does that answer your question?
Yeah, but I guess it can trigger a lot of other questions of what besides reasonable.
No, and that's the big... The way I'm deciding reasonable now is, and this is definitely a work in progress.
He's smiling on your right.
Yeah. No, this is a good... So the way I'm thinking of it now is, given a block, what you could do is order it by fees, and that could be a new consensus rule. And then in this opcode, it would basically say, look at the 20th percentile fee that was paid. Anything below that, if I'm willing to pay 5 cents, and there's at least 20% of the block that paid 5 cents or less, that's reasonable. So now there's this opportunity cost for the miner. This sort of, if they want to mess with the opcode, they'd have to give up 20% of their fees. So I'm working out, how viable is that really financially? So that's a work in progress at the moment. That's how I would define it.
Next question up here. My question is for Ren. Have you done research or simulations on the throughput increase that your protocol would offer?
It is ongoing. We have several very good developers working on that. But the developer said, which is surprising, he said, I think he lowered the block interval to 15 seconds. But if you lower the block interval to 15 seconds, in the current Bitcoin protocol, there are no orphans. So which means, and he managed to test a single client that our protocol can significantly reduce the block propagation time. So in order for our protocol to perform better than Bitcoin protocol, which I'm sure it will be, the block interval can be lowered to like 1 second or 2 seconds, which is crazy.
Question for Patrick. Great talk, both you guys. The pre-Lightning payment channels were pretty fascinating. I learned a bit about those today. With replaced by time lock, who determined the decrementing unit of time? So in your example, you talked about like a day each time.
That's like set by the... so normally the day is the example everybody uses, but that's decided between the two parties. And that's the risk you're willing to take. Pretty much I now have a 3-hour period to actually close the channel. And that's why they were really awkward, because people don't come online at the right time. So here's a good example, and this was with the Ethereum name service. They have this auction protocol. The first 3 days, I send a sale bid. The last 2 days, I open my bid, and people can see what I made for my bid. Most people couldn't do that. After 3 days, people just forgot they placed a bid, and they lost their money. So that's why replaced by time lock just doesn't work in practice, because people don't come in online within this weird time period. And I should mention one thing. So the Spielman channels, the one-way payment channels, they're very elegant. I really like one-way payment channels because they have this really nice property where the sender can go offline and they're still safe. So if Alice is sending coins to Bob with the one-way payment channel, Alice can go offline and Bob can't steal her coins because it's replaced by incentive. Bob will only ever broadcast a transaction that will pay him the most money, but he can't actually take any more money than he deserves. So one-way payment channels are really useful for like lots of protocols.
All right, I think that's it for questions. Obviously, people can chat more after. Big round of applause for our speakers. Thanks so much for coming out. Obviously, it was a little more technical than our usual talks, but I think it's definitely really important that we just keep, reminding people about how this stuff works and educating them. So thank you so much for explaining your ideas and the history around them. All right, and that's it for today. There's still some drinks and food in the back, I believe, and thanks for coming out.